Hi everyone, I am Oguzhan. Very happy and excited to be here and to be able to present our work BreakHammer, enhancing RowHammer mitigations by carefully throttling suspect threads. Here's an executive summary of my talk. DRAM continues to become more vulnerable to RowHammer, and operations that prevent RowHammer, which we call RowHammer preventive actions, are blocking operations that take too much time. We introduce a new exploit where one can mount a memory performance attack by triggering many of these actions and blocking access to main memory for extended periods of time. Our goal is to reduce the performance overhead of RowHammer mitigation mechanisms by reducing the number of performed RowHammer preventive actions without compromising system robustness. Our key idea is to throttle threads that trigger many of these actions. We introduce a new mechanism called BreakHammer that observes triggered RowHammer preventive actions, identifies threads that trigger many of these actions, we call such threads suspect threads, and reduces the memory bandwidth usage of suspect threads. Our results show that BreakHammer significantly reduces the negative effects of RowHammer solutions on performance, energy, and fairness. BreakHammer is open source and artifact evaluated, available through this link. Here's the outline of my talk. I'll start with a brief background on DRAM and DRAM lead disturbance. Here I show a typical computing system with a processor and a DRAM module connected through the DRAM channel. Inside the DRAM module, we have several DRAM chips, and inside the DRAM chip, we have multiple DRAM banks. A DRAM bank contains a two-dimensional array of DRAM cells, each of which containing a single bit of information as electrical charge. DRAM cells are horizontally organized as DRAM rows and connected via word lines, and they are vertically connected via bit lines to sense amplifiers for DRAM accesses. DRAM is accessed at a row granularity. However, today, this access is not perfect, where the access is vulnerable to read disturbance. Here I show a prime example of read disturbance called RowHammer, where repeatedly opening and closing a DRAM row induces bit flips in the nearby DRAM cells. In RowHammer terminology, we refer to the repeatedly opened row as the aggressor row, and we refer to the nearby rows that experience bit flips as the victim rows. We also denote the minimum activations necessary to induce the first bit flip as the RowHammer threshold, or NRH. DRAM modules are continuously becoming more vulnerable to read disturbance over generations. Over the last decade, we have seen more than 2 orders of magnitude decrease in the necessary activations to induce the first bit flip. Therefore, it is critical to effectively prevent these bit flips. There are many ways proposed in prior work to prevent RowHammer with what we call RowHammer preventive actions. Here I show a non-exhaustive list of actions one can perform to mitigate RowHammer bit flips. In our talk, we will focus on preventive refresh and row migration, as state-of-the-art RowHammer mitigation mechanisms tend to adapt these solutions. One of these ways is to preventively refresh the potential victims of an aggressor row before they observe bit flips. Another way is to move the contents of an aggressor row away to a distant row, away from its victims, before it has been activated enough times. I'll continue with the motivation of our work. One of the problems with RowHammer preventive actions is that they are blocking operations where the memory controller cannot access a memory bank undergoing the action. As such, refreshing kilobytes of data can block access to gigabytes of data. We analyze the system performance impact of blocking RowHammer preventive actions by evaluating 4 state-of-the-art RowHammer mitigation mechanisms. Here, the x-axis is the decreasing RowHammer threshold, y-axis is the weighted speedup normalized to a baseline with no RowHammer defense, and each bar identifies a different RowHammer mitigation mechanism. Here, Hydra, RFM, and Para use preventive refresh, and Aqua uses row migration. From our results, we observe that RowHammer mitigation mechanisms incur increasingly large overheads as the RowHammer thresholds decrease. Even worse, at lower RowHammer thresholds, RowHammer preventive actions become a potential memory attack vector, where an attacker can intentionally trigger many of these actions and deny access to main memory. Therefore, the problem we tackle is operations that prevent RowHammer lead to DRAM bandwidth availability issues, as they can frequently block access to memory. And our goal is to reduce the performance overhead of RowHammer mitigation mechanisms by reducing the number of performed RowHammer preventive actions without compromising system robustness. To this end, we propose a new mechanism called BreakHammer. BreakHammer's key idea is to detect and slow down attackers that trigger many of these preventive actions. In our study, we refer to such threats as suspect threats. Here I show a cartoonish execution overview of BreakHammer. BreakHammer divides the execution timeline into periods of equal length, which we call throttling windows, and views the execution as a stream of row activations from different threads and RowHammer preventive actions. Whenever a RowHammer preventive action is triggered, BreakHammer performs 3 key operations. First, BreakHammer attributes what we call a RowHammer preventive score to each thread, proportional to their contribution to the triggered RowHammer preventive action. Second, BreakHammer performs outlier analysis on the attributed preventive scores and detects suspect threats that unfairly reduce DRAM bandwidth availability. Lastly, BreakHammer slows down suspect threats by reducing their memory bandwidth usage. Now let's take a deeper look on how BreakHammer attributes RowHammer preventive scores. BreakHammer tracks a number of RowHammer preventive actions each thread triggers. To do so, BreakHammer implements a counter per hardware thread called RowHammer preventive score. The challenge with updating these scores is that one cannot directly attribute a RowHammer preventive action to a single thread because RowHammer preventive actions are generally caused by a stream of requests from many hardware threads. Here on the bottom, I show a timeline of DRAM activations and RowHammer preventive actions, where a stream of row activations from multiple threads trigger a preventive action. When a preventive action is triggered, BreakHammer attributes a score to each thread proportional to the number of activations they performed to cause the action. BreakHammer cooperates with existing RowHammer solutions. Therefore, observed RowHammer preventive action changes depending on the mechanism BreakHammer is integrated with. Here I show two examples on how BreakHammer can be integrated with existing solutions. Our first example is a memory controller-based mechanism called probabilistic row activation, or PARA for short. In systems protected with PARA, whenever a DRAM row is activated, PARA generates a random number and compares it to a threshold. If the random number exceeds the threshold, PARA performs a preventive refresh. When we integrate BreakHammer with PARA, BreakHammer tracks the row activation count of each hardware thread between preventive refreshes, and whenever a preventive refresh is performed, BreakHammer increments each thread's score proportionally to their number of activations. Our second example is an in-DRAM solution, which is the latest industry solution to DRAM leak disturbance from JEDEC, widely known as PARA activation counting, or PRAC for short. With PRAC, DRAM maintains an activation counter per DRAM row, and whenever one of these counters reach a critical value, for example, close to the RowHammer threshold, the DRAM module triggers what's called a backoff. After a backoff is received in the memory controller, it stops performing main memory accesses and starts sending special commands to allow time for preventive refreshes. When we integrate BreakHammer with PRAC, BreakHammer tracks the row activation count between backoffs, and when a backoff is triggered, it similarly to PARA, increments each thread's score proportionally to the number of activations each thread performed. BreakHammer is compatible with a wide variety of solutions, both in memory and in memory controller, as we have seen. In our paper, we integrate BreakHammer with 8 state-of-the-art RowHammer solutions. I would like to refer you to our paper or our GitHub repository for their implementations and integrations. Let's continue by looking at how BreakHammer detects suspects. BreakHammer identifies suspect threats by detecting threats that trigger too many RowHammer preventive actions. Here on the left, we have the RowHammer preventive scores of threads in the system. We can visualize these scores as a distribution where each bar identifies shows a different thread, and the height of the bar shows their score. BreakHammer detects a suspect thread with two checks. First, BreakHammer checks if the thread score exceeds a minimum score to consider. This allows BreakHammer to protect threads with low memory intensity. Second, BreakHammer checks if a thread score exceeds the average score largely. Doing so allows BreakHammer to detect suspect threads that unfairly reduce DRAM bandwidth availability. Lastly, let's look at how BreakHammer slows down memory accesses. There are many ways to reduce the memory bandwidth usage of a hardware thread. For our implementation, we chose to limit the allocatable cache miss buffers in the last level cache. These buffers track the memory requests that miss the last level cache and are currently absorbed by the main memory. At system boot, all threads have 0 allocated cache miss buffers, and if they need to, they can allocate all of the cache miss buffers. As the systems execute and threads start making memory requests, they start using these cache miss buffers. When BreakHammer identifies a thread as suspect, it limits the number of cache miss buffers the thread can allocate. If a thread reaches their allocation limit, the thread can no longer make new memory requests and must wait for their earlier requests to be resolved. BreakHammer restores the memory bandwidth usage of a suspect thread if the thread stays benign for the whole duration of a throttling window. Here on the bottom, I show a timeline for an example where, in our example, the thread gets identified as a suspect and BreakHammer immediately throttles their memory requests. On the second window, the thread continues executing with the reduced memory bandwidth, where the thread stays benign and does not get identified as a suspect. At the end of this throttling window, BreakHammer observes that the thread stayed benign and removes their memory bandwidth usage quota. Where in the last window, the thread continues to stay benign and uses its full memory bandwidth. Now I'll continue with the evaluation of BreakHammer. We evaluate BreakHammer with cycle level simulations using Emulator 2.0 integrated with DRAM power. We simulate a realistic 4-core system with a DDR5 module that has 2 ranks and 64 banks in total. We integrate BreakHammer with 8 state-of-the-art RowHammer mitigation mechanisms and compare BreakHammer paired versions of these mechanisms against their baselines without BreakHammer. We evaluate a wide variety of workloads from 5 major benchmark suites. We create 2 types of mixes, where in 90 mixes, we have a non-malicious core mounting a memory performance attack by triggering many RowHammer preventive actions. And in 90 of the mixes, we have all cores as benign. Let's start by discussing systems that are under attack. We first take a look at BreakHammer's impact on the number of preventive actions performed. Here, the x-axis is the decreasing RowHammer threshold. Y-axis is the preventive action count, normalized to a system, normalized to the preventive count of the system without BreakHammer at a RowHammer threshold of 4K. The blue line identifies the system without BreakHammer, and orange line is the system with BreakHammer. As an example, this point shows that Preg performs approximately 34 times many more preventive actions when the RowHammer threshold decreases from 4K to 128. And in the same threshold, if we pair Preg with BreakHammer, we see an 80% reduction in the number of preventive actions performed. When we look across all of our results, we observe that BreakHammer significantly reduces the number of preventive actions across all mitigation mechanisms and all thresholds. We continue by evaluating BreakHammer's impact on memory latency. The x-axis is the memory latency percentiles. The y-axis is the memory latency of benign workloads in nanoseconds. The blue line shows system without BreakHammer, the orange line shows the system with BreakHammer, and dashed black line shows the memory latency of a system with no RowHammer defense. As an example again, this point on the blue line means that when we have Preg, 50% of requests are served within 200 nanoseconds. When we look at all of our results, we observe that BreakHammer reduces the memory latency of all evaluated mitigation mechanisms across all percentile values. We analyze the reduced RowHammer preventive action count and improved memory latency effect on system performance. Here, the x-axis is the decreasing RowHammer threshold. Y-axis is the weighted speedup of benign applications normalized to a system with no RowHammer defense. And bars identify mitigation mechanisms with and without BreakHammer. From Preg results, we see that BreakHammer significantly improves performance. And when we look at the trends across all evaluated mechanisms, we first see that as the RowHammer thresholds decrease, all mitigation mechanisms incur more overhead, and pairing them with BreakHammer has significant performance benefits. We also evaluate BreakHammer's impact on DRAM energy, where the x-axis is the decreasing threshold, y-axis is the normalized DRAM energy to a system with no RowHammer defense, and bar similarly shows systems with and without BreakHammer. In Preg, we also see that BreakHammer significantly reduces DRAM energy, and when we look across trends on all mitigations, they induce more DRAM energy consumption as the thresholds decrease, and pairing them with BreakHammer, again, has high energy benefits. To summarize, BreakHammer significantly reduces the negative performance and energy overheads of existing RowHammer mitigation mechanisms when a memory performance attack is present. We attribute these benefits to BreakHammer accurately detecting suspect threats, and BreakHammer effectively reducing the memory interference caused by suspect threats. I'll continue by summarizing our benign workload results. Across 94 core benign workload mixes, even though it is not our goal to improve the system performance of benign systems, we observe that BreakHammer slightly improves memory latency, system performance, and DRAM energy efficiency of benign workloads. I would like to refer you to our paper for more details on BreakHammer's implementation, such as resetting BreakHammer's counters or tracking software threats, our security analysis, where we have an upper bound on the overhead an attacker can cause, and security against multi-threaded attackers that try to circumvent BreakHammer, and lastly, more performance evaluations such as unfairness, sensitivity to memory intensity, and comparison to other techniques. BreakHammer is available on archive, accessible through this link or the QR code. Now I'll conclude my talk. We introduced the idea that one can mount a memory performance attack by triggering RowHammer preventive actions to block memory accesses for extended periods of time. We propose BreakHammer, which observes triggered RowHammer preventive actions, identifies threats that trigger many of these actions, and slows down their memory accesses. Our results show that when an attacker is present, BreakHammer accurately throttles the attacker, which significantly improves performance and reduces energy. And when all applications are benign, even though it is not BreakHammer's goal, it slightly improves performance and reduces energy consumption. BreakHammer is open sourced, and all of our datasets are available online and artifact validated. Thank you for listening to my talk. I would be happy to have any questions you may have.